The next problem that we wish to tackle is problem 179, which goes like this. You see, let's have a look at the picture first. What we see here are rings which have got holes in the middle, and some of them are stacked on the ground, and one is standing vertically over the others. All right, so what kind of a problem is this? The certain type of ring, its outer diameter is 15 millimeters. So it is given that the diameter of this ring, the outer diameter, in other words, from that end all the way up to this end, that diameter is 58 millimeters. So the radius of this outside, the outer radius is 29 millimeters, which is half of that. Okay. The inner diameter is 40 millimeters. So in other words, if you take the diameter of the inside circle, it's 40 millimeters. Now you will see that these rings are stacked on top of each other. So this ring which is on the floor is also 40 millimeters in diameter. And a little bit of thought will tell you that where this thing is touching, you see this top ring where it touches, try to put it there somewhere. And if you join it to where it touches on this side, that line will have to be the diameter of the small circle, because when you rest this top ring on this, it will have to go right through the middle. It wouldn't, otherwise it wouldn't balance like the way it's done. So that is the diameter from there to there. All right, if one stacks, oh, the thickness is 1 millimeter. So this thing is, all these are 1 millimeter thick, or if you want to look it down here, all these are 1 millimeter thick downwards. Now, if one stacks enough rings on top of each other, it is possible to stand another ring vertically on top of the file in such a way that the ring just touches the bottom. So you see this part here underneath this blue line, that's the part which is inside the hole. And you want this thing to just touch the bottom, to go to the bottom of that. So you can imagine that the bottom of this is touching the floor, or otherwise at the bottom of where these rings are. Right. Okay, so that's the story there. Now the question is now, how many rings are in the stack when this happens? In other words, when this outer ring just touches the bottom, how many rings are there in the stack? Interesting problem. So let's have a look at what's going on. Okay, so what we've got here is so let's have a look at this picture here. This is a vertical cross section of this. You know, what I showed you earlier on. So this part here is a ring that is standing, and this part here is the diameter of the inner ring, as I pointed out earlier. So this AB is the diameter of the inner ring, and we know what that is. That is equal to 40 millimeters. It's given that that's 40 millimeters. All right. Now, this thing here, maybe we should say, is the vertical ring. And these rings are placed in such a way, you see, this is just C and D. We are not showing the rings in between. I'm showing it here. I'm showing the bottom picture. So there are several rings here, like this, and this is the ground. So they want to know how many rings are there stacked up. So what you're looking at, the number of rings, they're all sitting on top of each other. And we know that the thickness of each ring is 1 millimeter. One millimeter thick. So if you want to know how many rings there are, you have to know what is this distance from C to D. If you know how many millimeters there are from C to D, then you know each one is stacked on top of the other, as we can see. And if that distance is 6 millimeters, if you know that distance, then you know that each one is 1 millimeter thick. That means you'll be able to calculate. So what we are doing here is this part here is your CD that we are speaking about, right? Because this part just touches it. All right, so let's go ahead. Now, what's the geometry of this? This is the diameter of the inner ring. So what we do is we join the center of the top ring and go right down to the bottom to the ground. So we need to calculate CD. So let's see what we have to do. We need to calculate. If you know CD in millimeters, then you'll know how many rings there are because each one is 1 millimeter. And all you have to do is to say how many millimeters there are in CD is exactly the same as how many rings there are because each one is 1 millimeter thick. Okay, so how do we calculate this? Now, CD we don't know, but what we do know is that AB is 40. Now, this thing here is vertical downwards. This is the way it touches is really the tangent. So we can say that this is tangent and this is horizontal. So the so this angle here is 90 degrees, as you can see, because this is perpendicular to this, to the tangent, and this is parallel to this. So this must be 90 degrees. But now you know that when you go to the center of a circle and you join it, it's perpendicular. You draw a line which is perpendicular to a chord, then it divides the chord into two equal parts. Right? This is a theorem, right? The center of the circle is if you draw the perpendicular from the center of a circle to a chord, it bisects the chord. In other words, this line here is a perpendicular bisector of a chord. In fact, the perpendicular bisector of any chord, it goes through the center of the circle. It's a nice exercise to prove. All right, so that is why we can say that this is 20. The whole thing is 40. This part here is 20. Okay, now to calculate CD, why don't we try to calculate the whole of, well, OD we know. That's the radius of the large circle. And the diameter of the large circle is 58. So the radius of the large circle is 29, which means that this distance from O to down to D is 29. Okay. So, but it's also the same as the radius. So this is also 29. And now you have the theorem of Pythagoras kicks in because you've got a right angle triangle here. This is half of 40. That's the radius. And when you calculate OC, by Pythagoras, OC squared is 29 squared, the hypotenuse squared, minus 20 squared, right? The OC squared plus 20 squared is 29 squared. Now you're not allowed to use a calculator, but you can do this thing very quickly if you use it as a difference of two squares. 29 minus 20 into 29 plus 20, that gives you 29 plus 20 is 49. So OC squared is 9 times 49. So OC will be the square root of that, which is 3 times 7, which makes this thing 21. All right. So OC is 21 millimeters. Everything is in millimeters. So this length here is 21 up to that point. And the whole thing is 29. So there we have it. We can see CD will have to be 29 minus 21, which is 8 millimeters. So CD is 8 millimeters. And so how many 1 millimeter stacks do you need? Rings do you need to fit in 8 millimeters? The answer is 8 such. 8 rings on the base. This is a base that we had a picture before. So how many rings are there? This distance here is 8 millimeters. Each ring is 1 millimeter thick. So there are 8 such rings. Right. So that's the answer to that problem. We go to problem 354 of the book. A hexagon is inscribed in a circle. 3 of the sides have length A and 3 have length B. So hexagon is a 6-sided figure, and 3 of the sides have equal length A, and the remaining 3 have length B. The question is, determine the radius of the circle in terms of A and B. So let's have a look at what this is saying. So we have a circle and an hexagon is drawn inside it. So let's just try to draw the circle. So you're drawing a 6-sided figure inside this circle, but 3 of them are the same, right? So so let's draw the 6 again. 1, 2, you got a short one. 3, another short one. 4, so that makes 3 short ones, and then 2 long ones. The A and B. So you got different 2 different lengths. So if we call this length here A, all the small ones are A, and there's a B. So it says that 3 of the sides have length A and 3 have length B, and this hexagon is drawn inside the circle. So this is what we've got here now. Okay. The question is to find the radius of the circle. Right, so let's draw the radius. But first you have to choose some point as the center. So if the center is here somewhere, so let's draw the radius. Let me use another color. So from the center of the circle, if we draw the radius, we can draw all the 6 radii. All these are the same because this is the center of the circle. Okay, so you need to find this R here. You need to find the radius of the circle. Let's give it a name. We'll call it R. And so that's a question. Okay, so how do you go around doing this? Well, for one thing, you got equal chords. You got three equal chords, and equal chords subtend equal angles at the circumference. One of these, two of the sides of the hexagon adjacent to each other should be of one is A, one is B. Let's take that vertex where one side is B, and the other side is A. There will always be such a vertex. So let's take that vertex as the one that we got in this figure. And then we need to find the R. So how do we go around doing that? Well, I got a small quadrilateral here, and this is R here as well. And I have a quadrilateral with two sides A and B. We need to find R in terms of A and B. But what do we know? We don't know much about this. But we do know that if this angle here is alpha, so alpha is the angle subtended by A at the center of the circle. Equal chords will subtend equal angles, not only at the center, but also at the circumference. Because the angle at the circumference is half the angle at the center. So if the angles at the circumference are equal, the angles at the centers are also equal. All right. So suppose A subtends angle alpha at the center, and B would evidently subtend another angle beta, say, and of course equal all chords subtend equal angles. So these all will be beta. The three B's and the A will subtend alpha. So now we have an interesting relationship here at the center, namely that the sum of these angles at the center, the three alphas and three betas, and these six angles together add up to 360 degrees, right? Which means that alpha plus beta is 120 degrees. Now that's very useful because that is an angle here. This is alpha plus beta. And that angle, we just now calculated it to be 120 degrees. Okay, so that's fine. Now we've got a quadrilateral. Two sides are A and B, the other two sides are R. And we've got this angle. Do we know anything else about this quadrilateral? Now, interestingly, yes, we do know something else about this quadrilateral, namely, I can calculate this angle here. See? Now, you might ask, how can I calculate this? But I'll show you. Let's go to this picture here. And here you see, I've drawn this picture here again. You got BA. This angle here was 120. Now, if you look at this picture here, you will see that this chord, it subtends an angle of 120 degrees on this side. And if I take any point on the other side, you got a cyclic quadrilateral, and 120, if this is 120, this will have to be 60. Because the opposite angles of a cyclic quadrilateral are supplementary. So this angle here will be 60 degrees. Right? And if that is 60 degrees, then this angle here, angle at the center, is twice the angle at the circumference. So this chord here, it subtends 60 degrees, so it must subtend 120 degrees here. Okay. Another way of doing this is that this is 120, so that angle, that reflex angle, will have to be twice. That will be 240, and therefore the remaining one will be 120. But the point is now, I can actually calculate what R is. Right? And you might be quite surprised that you can calculate R from this situation, and the answer is this line here. Let's call this xy. You can calculate xy squared in two different ways using the cosine formula. Xy squared in this triangle here, you got two sides and an included angle, AB. So if you use the cosine formula, I don't know whether you're familiar with it, but it says that the square of any side of a triangle is the sum of the squares of the other two sides, but you have to subtract from it minus 2AB cosine of the included angle. So it's minus 2 times that AB times the cosine of the included angle. Right, but xy squared, now this, if you, the cosine of 120 degrees is the negative of cosine 60 degrees. Because this angle is in the second quadrant, the cosine in the second quadrant is negative, so it would be minus 6 cosine 60 degrees. Cosine 60 is a half, so this is minus 2AB, cos of this is minus half, and when you simplify that, you get a squared plus b squared plus AB. Nice answer. Minus 2 times minus half is plus 1. But xy squared is also, if you look at the other side, again, you got a triangle, but the sides are R and 120 degrees. So you can do exactly the same thing to this side, and you'll get that xy squared is R squared plus R squared minus 2AB is RR cos, and again you get 120 degrees, same angle. And again, the minus 2 cos 120 becomes plus 1. So you'll have R squared plus R squared plus R squared. So you get 3R squared. So these two represent the same thing. So it means from here, you can make these are equal. So you can calculate this is equal to this. So R squared is equal to A squared plus B squared plus AB divided by 3, because both of them are equal to 3R squared. But you're calculating R, so it has to be the square root of that, which gives R in terms of A and B, as was required. The next problem is problem number 816. It reads as follows. The figure alongside shows two concentric circles. Concentric means that they have the same center. If the area of the ring between the two circles, so you can see the ring here, it's called an annulus, A-N-N-U-L-U-S. If that area is 144 pi, so it's given that the amount of space occupied by this area here is 144 pi square centimeters. What is the length of the tangent, this tangent, PD, in centimeters? So the question is, what is PD? There's only one piece of information given, namely the area of this. And you're asked to find PD. It looks like a very interesting problem, because there's so little information given. Okay, so where do we start here? Well, we need to calculate PD. This distance from here to here. Okay, now this thing is tangent to the circle, and when you got a tangent to a circle, as we said earlier on, when you join the point of contact to the center of the circle, this thing becomes a right angle. It becomes 90 degrees. All right. So we need to find out what PD is, but then we also know that when you join the center of a circle and you draw it perpendicular to a chord, now this is a chord in the large circle, and this is the center of the large circle. Both the circles have got the same center. And so it means that this must be bisected. And that's a theorem, one of the early theorems you do in circles. And also you have that if you join this to the center of that chord, it will be perpendicular. So if it's perpendicular, it's bisects, and if it bisects, it's perpendicular. Because that's a very important theorem. Okay, so we need to find the radius of this. We need to find this. So we don't know what this is. Let's call it x. Okay, so this one, we don't know that too. That's the radius of the small circle. So let's call it small r. And also, now you see, I've got a kind of a right angle situation here. So it seems that we can use Pythagoras, but we have to join that, which is the hypotenuse. And when you join that, you can see clearly that this is the radius of the large circle. So you got the radius of the large circle and you got the radius of the small circle are given names. And we are now asked to calculate x. So Pythagoras kicks in because you've got x squared is equal to the hypotenuse squared minus r squared. Okay. Now it's given that the area of this ring, this entire area, is 144 pi. So we've got 144 pi is the area of the ring. But the area of the ring is just the area of large circle minus the area of the small circle. If you have to calculate the area of this red part, you simply remove the middle part from the whole. So that means the area of the large circle, take away the area of the small circle. But the formula for the area of a large circle is pi r squared. And what is the radius of the large circle? It's capital R. So the area of the large circle is pi r squared. And the area of the small circle is pi times its radius, which we know to be r. So you got the pi comes out as a common factor. So what do you have? On the other side, you got 144 pi. The pi's cancel. And you have that r squared minus small r squared is 144. Right, you got a nice thing. But this is exactly what we were looking for. Right. We're looking for capital R squared minus small r squared. And that is your x squared. So your x, if x squared is 144, then x must be 12. But as we saw, PD, this is what we wanted. What is the length of PD? And that is 2x. Because the center of a circle, when you join it, when it's perpendicular, it bisects it. And we know that x is 12, so PD must be 24. And the problem was given in centimeters. They said that the area is 144 square centimeters. So the answer to the question is PD is 24. Before we tackle the next problem, I just want to recall 3 theorems which will be useful in solving the next problem. It says the following: if the opposite angles of a quadrilateral are supplementary, the quadrilateral is cyclic. I think we've already been through that. The next one here, which we haven't done before, is if you got this situation here, you got 2 lines which are parallel, and you got 2 other lines which are shooting out at the same angle from this parallel line. It means these two new lines, they make the same angle with these 2 parallel lines. You can make a conclusion from this. The conclusion being that these 2 lines here, right, they themselves have to be parallel. See, that's a conclusion. And if you want to know why, it's not difficult to prove. All you have to do is extend this line. And you want to show that this line here is parallel to that line. When you extend it, then you can see quite clearly that these 2 lines were parallel, so this becomes theta here. They become alternate angles. But the moment this is theta, then you'll see that you got this diagram. So these 2 angles now become alternate angles and they're equal. So if alternate angles are equal, the lines themselves are parallel, right? And the last one, which we have already done, very extremely important. If you got a quadrilateral and you got a figure like this, it means that one of the sides subtends equal angles at the other 2 points. So that forces this quadrilateral to be a cyclic quadrilateral, forces it to have the property that a circle goes through all 4 points. The moment you have that, then the 4 sides become four chords of that circle, and each of those chords will subtend equal angles in the same segment. And this is what you have at the end of it all. All right, so let's go to the problem now, which we want to tackle. All right, so this problem says that ABDC is a parallelogram. So the outside figure is a palm. E is an interior point, it's inside, such that the angles AEB angle AEB, that's AEB, and CED, let's call it Y, are supplementary. So it's given that x plus y is 180 degrees. They are supplementary. All right, so that is given. So what is the question? The question is, prove that angle ECD, that's ECD, equals angle EBD. So the problem is, are these 2 angles equal? Very strange question, because you just have a parallelogram outside, and you have the strange property that this angle and that angle, they are supplementary. Okay, so this is not a trivial problem. It's quite a demanding problem, but it's got a very simple sort of background to it. It's a very simple picture, no complicated picture. And you have to show the 2 angles are equal. When you try to do the usual kind of things, chase angles, take alternate angles, you're not going to get anywhere, because this is quite it's much deeper than that. All right, so let's see now, how does one go around tackling a problem like this? Okay, so what we have here is that these angles are supplementary. That's all we are given. This is x and this is y. It's given that x plus y is 180 degrees. You notice I'm not writing out the proofs, and the writing out of the proofs is a very important exercise. I am simply telling you how to do it, and after that, you should give yourself enough practice on writing out proofs and writing out the solutions. And each time you write something, you must make sure that you give in brackets on the side the reason why you're making a statement. You have to state the theorem, right? There are certain shortcut ways of stating the theorem, but whatever it is, even if you state it in in fullness, that'll be fine. So this is what is given. Now, how do you make use of a thing like this? Well, a little bit of thought, you'll see that what I have to do, if I want to use x plus y supplementary, it looks as if we have to use the fact that opposite angles of a cyclic quadrilateral supplementary. But there's no cyclic quadrilateral. So how do you do this? Well, you can make this angle here opposite to this angle in a quadrilateral. Now, how do you do that? What you have to do is take this triangle at the bottom, cut it, and paste it on top of AB. See, CD and AB are exactly equal. So I can take this, cut it, and when I push it up here, right, I'm going to paste it out there. So the same triangle is here now. I've just pushed it up there, which means that the triangles are congruent because I didn't do anything to it. I took exactly the same triangle and put it back there at the top, right? Now, why did I do that? The reason is now this y here is now there, and now you have a quadrilateral. You see this ABC, let's call this E. ABCE is a quadrilateral where the opposite angles, x plus y, is 180 degrees. So this becomes a cyclic quadrilateral. Okay. All right. And in a cyclic quadrilateral, I've got one diagonal already drawn. It's always useful to draw the other diagonal, as we saw. Right. Now, let's just go back to what we were asked to prove. We were asked to prove that this angle here is equal to this angle there, which I'm pointing to. All right, let's see whether we can get there. These two triangles are congruent because all you did was cut this thing out and pasted it up there. So everything remains the same. Those become equal. Those become equal, and all the other things that go along with it. Right? And also, we know this angle here. Right? So the third angles are equal. Right? Now, you have that this quadrilateral now is cyclic because the opposite angle is supplementary. So therefore, this angle here is a dot because EB will subtend equal angles at the other 2 points. One of them is a dot. So you have to see what it subtends again. It subtends that angle. So this is a dot. Now remember, we are trying to get to this angle here. Now you have this picture which I told you before. These two lines are parallel. And you got the same angle repeated on the top there. And I told you the conclusion from that is that these two lines will have to be parallel. Right. Now, I forgot to mention an extremely important theorem. The theorem is if one pair of opposite sides of a quadrilateral, hopefully you did this in the last geometry lesson. If one pair of opposite sides of a quadrilateral are equal and parallel, the quadrilateral is a parallelogram. We use the symbol PARM for a parallelogram. Right, so if you have a picture where one pair of opposite sides are equal and parallel, the whole thing is a parallelogram. And you've got it here. You got that. If you look at these four vertices, I shouldn't have called this, I should have called this something else, F. Those four vertices, you see that one pair of opposite sides are equal because of congruency, and they are parallel. We just showed it's parallel. So therefore, this figure here is a parallelogram. But the moment it is a parallelogram, it means that you got another pair of parallel lines here like that, because this whole figure is a parallelogram. The opposite sides now become parallel. And if you look at this dot here, which I stopped at earlier on, that becomes an alternate angle to that one, lo and behold. So this angle here is actually equal to that angle by chasing this diagram like this. Okay, so that brings an end to that problem. We have time for maybe just one problem, and I'm going to now do a problem on similar triangles, because we said we're going to do circles and similar triangles. And yeah, to this end, similar triangles are triangles which have the property that the two angles of one triangle are equal to two angles of the other. Actually, it's all the angles of one triangle are equal to all the angles of the other. But if you got two angles of one triangle equal to two angles of the other triangle, the third angle will automatically be equal because they all add up to 180 degrees. Right. And the very nice thing about similar triangles is that because of that property, the one is just an enlargement of the other. So then you have a kind of a proportionality thing. You know, if you got two triangles and they are similar, means you got the same angles. Then you can sort of intuitively see that this is like a baby triangle of this. It's exactly the same. It's got the same angles. So I can push this triangle and slide it to be inside this larger triangle. And if you slide it, from what we said earlier, if you're sliding it without rotating it, you will have these angles. These lines are parallel. Because you're just sliding it. And these angles are equal. Y, Z, Z. And from what we said earlier, if you got, you will see that these lines now become parallel. This line is parallel to that. No, of course, they are parallel. What I wanted to say is that you can see this is just a small version of the large one. In other words, it's like a photograph. The small guy is a photograph of the big guy. And with a photograph, these things, the one is just a stretch of the other. In other words, if this thing here is double the other one, the ratio of this side to that side will be the same as the ratio of the other corresponding sides. This over R. So, and this is a very important property of similar triangles, that their sides are in the same proportion in lengths. A over P is equal to B over Q is equal to C over R. And conversely, if you have two triangles whose sides are in the same proportion, like this, then their angles are equal. They are similar. So that's the most important theorem in similarity. And there are some other theorems, mean proportion and so on, which we are not going to discuss here. All right, so let's get going with this problem. It's given that you got a very simple picture. You got a triangle like this, and it's given that this angle A is twice this angle. In other words, if this is theta, this angle here is 2 theta. That's what's given. And you're asked to prove this relationship between the sides, that if you square this side, you're going to get B times B plus C. That is provided that this angle, one angle, is twice the other angle. You can make this conclusion, and you're asked to prove it. Now, the question arises, how do you go around doing a thing like this? This looks very complicated. But the answer is in the question, because you got a B plus C here. So why don't we try to draw a line which is B plus C long? You already got a B, right? To get a B plus C, all you have to do is to extend this line. You extend it by its same length. Keep going down like that until you get C, this C formed here, right? Then you will have your B plus C. So this long line here will be B plus C. So you have at least one line whose length is B plus C. All right, and this is what we are going to do in this next picture. As you can see, what I've done is taken this line here and extended this through this length C. Now remember, we said that this angle is theta and this angle is 2 theta. All right. Now we've got a situation where we've got the B plus C and everything, and we want to see whether we can get to that equation which was given. Let's look at the picture here. If you look at this picture here, you will see that this triangle here is isosceles, C and C. So therefore, these two angles are equal. But when you double this, if these angles are equal, then when you add them, you're going to get that one there, because that's the exterior angle of a triangle theorem. The exterior angle is equal to the sum of the interior opposite angles. So 2 theta is equal to the sum of these, but they are equal. So each of them is now forced to be equal. And There you have it. You have similar triangles. Now, how come? Well, let's repeat. If you look at triangle ABC, two of its angles are theta and 2 theta. But in the large triangle, two of its angles are theta and 2 theta. So in order to get the right proportion, what I normally do is I redraw these triangles. Right? So I take the small triangle, and this is 2 theta, and this is theta. Put a C here, put an A here, put a B here. So you have the same vertices on this triangle. Now let's draw the large triangle. Sorry. Let's draw the large triangle. Right? And what happens here now? The theta angle is at D. This is a theta. So let's put the D there and put theta here. Right. So the theta angle is at D, and the 2 theta angle is at B. So let's put 2 theta here, put a B here. Right. So the large triangle is DBC. So you got DB, and the C is as before. Right. Okay, so now these two triangles are similar. Now let's see if we know the sides. BC is equal to A, and there's a BC here also. So that'll be A. And CD is B plus C, because this is how we calculate it. This is by construction. CD is B plus C. Right? What else do we know here? We also know that CA is equal to B. So this part here, CA, is equal to B. So you've got these two triangles, and you've got the sides and so on, and you have these angles at theta and 2 theta. These triangles are similar, right? So you normally write it down like this. A, B, C is similar. You'll put 3 vertical lines and get the vertices in proportion. So you got A, B, C, they must correspond. Will be B. B is at 2 theta. Put a B here. And you got A, B, C, and B, A, B, B is at theta. So that will have to be D. And there you have it. So it'll be BDC. But in any case, if you got this, then the ratios come out very quickly, because if you write this thing correctly, this is a triangle. If you write it correctly the way I've done, the equal angles must be at the same places. Then you can get all the ratios very quickly. You take the first two, AB over BD. Then you take the second two, BC over DC. And then you take the extremes, AC over BC. You can write those 3 ratios just like that without even looking at the diagram. AB over BD equals BC over DC equals AC over BC. Right. But in this case here, I don't need all that, because here I can see the sides are A over B plus C. This over that equals that over that. So B over A. And if you cross multiply, you get A squared, A times A is equal to B into B plus C. If you go back, you will see that this is exactly what was required. That A squared is equal to B into B plus C. Okay. And the interesting thing about this, I want you to go and actually look at this problem in the book, problem 379, because this has got a converse as well. If you've got a triangle which has got this property, then you can prove that the one angle is twice the other angle. So that can actually be proved. And in fact, I have many ways of doing it, if I recall correctly. So it is a very fruitful business to try to prove the converse. In other words, if you are given that A squared is equal to B into B plus C, can you prove that angle A is twice angle B? So very challenging problem. And I have several solutions for that. Okay, in my book. So that brings me to the end of this meeting. Thank you very much for listening. And I hope you enjoyed the geometry in this. And I hope you also have learned that it's very important to know all the theorems so that you'll know when to apply them. Thank you very much and good night.